We are glad to have Dr. Saha as our speaker today. So Shayan did his undergrad in Kolkata University in Narendra Ramakrishna Mission, and then he went to ISA for integrated PhD, where he first finished his master's and then started doing his PhD. His PhD advisor was Professor Tarun Shorodip. And in his PhD, he worked on anisotropy of the CMB observations due to the observer's motion, that is our motion, and then later detection of galaxy clusters through CMB lensing. And he also had to sort of be in 3 different institutions for his PhD because Professor Shorodip moved to RRI as the director during his PhD tenure. So he was partly a fellow at RRI as well. And also he got a Swiss government excellence fellowship as a pre-doctoral fellowship and spent 1 year in Geneva. So in 3 different institutions. After finishing his PhD, he went to Northeastern University for his postdoc, where he's working on, again, detecting galaxy clusters using weak lensing. So we had a lot of discussion because he's
Boston.
About Boston addresses and so on. Okay, so and he's working on this data from this balloon-borne instrument named SuperBIT. So so let's hear from him.
Thanks a lot. Thanks for the introduction. So yeah, I'm Shayan. I have been here for in 2023, I gave a talk, and so it's really nice to be here again. So I'm from Northeastern, and today I'm here to talk to you about this mission called SuperBIT, where we mapped dark matter from Stratosphere for the first time. This mission, this collaboration is based on few institutes, as you can see in the logos. University of Toronto and Princeton actually built the instrument. JPL in Caltech and Northeastern is leading the data processing. And Durham University, and partly JPL as well, is focusing on the science goals with the data that we process. And NASA funded the flight. They funded the balloon that we used for its launch. Okay. So before I move on, please feel free to ask any question at any point. So this should be an interactive talk than like me just talking. Okay. So the talk is outlined as follows. So in this first part, I'll give you an overview about the mission, what this SuperBIT about, how did it launch, and basic details of the telescope. In the second part, I'm going to talk about what did we observe, like what was our strategy and what is exactly weak lensing of galaxies. I'll give you a very brief introduction of weak lensing. Third part, I'll talk about the data processing pipeline, which I worked on. That's the main work that I have done in this whole story. And finally, some science goal to complete the story, to go to the finish line. Okay, so I present to you Super Pressure Balloon-Borne Imaging Telescope, aka SuperBIT. As you can see from the name, it's separated in 2 different things. One is the super pressure balloon. It's made of polyethylene film. It's roughly thickness of a plastic wrap. When it's fully inflated, it's around 40 million cubic feet, which is equivalent to a whole football stadium. It cruises at 36 kilometers of altitude, and it can withstand almost 100 days of flight. The second part is the imaging telescope, which is flown with this balloon. I'm not going to go into the details of the telescope. I'm just going to give you some important feature here. One is its 0.5 meter mirror. Second is its 6 onboard filters. It has 6 filters from UV to near infrared, from 300 nanometer to 900 nanometer. It has captured the sky in 5-minute exposures. And during this 5-minute exposures, it had 0.05 arc second of stability. What that stability means, if I had to give you an intuition about the stability of this telescope, I would say, imagine looking at the CN Tower at in Toronto from this kind of distance, almost 2 kilometers away. The stability during this 5-minute exposure would be equivalent to a tip of a pencil held by someone at the top of the CN Tower. So that's how stable the telescope is over 5-minute exposures. And it's really important. It's really important to be that kind of stability, to have that kind of stability, to have any weak lensing data, any shape measurement happen in later down the pipeline. Okay. So let's talk about why did we observe from stratosphere? What are the advantages? So this is one photo taken from its observing condition, the sun, and as you can see, the first hint is the sky is very dark, which you will not get from the ground. So, like I said, it cruises at 35 to 45 kilometer of altitude, and that's why it's above 99% Earth's atmosphere. That's why the sky brightness is really low, because there is less scattering happening. The observing conditions, as I said, is very, very stable, and the transmission is very high. The plots that you see here are like just transmission in the telescope for different altitude. And at 38 kilometers, as you can see, we have good transmission throughout the wavelength range that we had. So the main point here is that it offers almost all the advantages of a space-based telescope while being very accessible like a ground-based telescope. And I'm going to talk to you about the accessibility in a moment. So yes, this is what I mean by accessibility. Because it's a balloon-borne telescope, you can fly it and then recover the platform. And that's why you could do multiple test flights with which we could upgrade the telescope platform, the imaging telescope itself multiple times. And we also had the cost in our favor. The mission only costed $5 million, and it was mostly built by graduate students at Toronto and Princeton. And if I had to give you a quick cost comparison, this is actually made by one of my students at Northeastern, who's currently at Cambridge, George. So he made this nice comparison. So if you had funding for one Vera Rubin observatory, you could build 100 SuperBIT with that. If you had funding for one Hubble telescope, you could build almost 1,500 SuperBIT with that. So this is the video of the flight of 2023 science flight from Wanaka, New Zealand. I hope this works. Okay, good. So this is the super pressure balloon as it's going up here. And the imaging telescope is here. So this is how it looked like when it was fully inflated, as you can see.
So this was flown from New Zealand?
Yes, Wanaka, New Zealand. Yeah, so a brief overview about the flight itself. It was launched in April 15, 2023. It observed 45 nights. It couldn't withstand 100 days of flight, unfortunately. So we had to shorten our observation strategy. It flown mostly around the South Pole, as you can see, and it flown actually opposite to the Earth's spin. Flight ended in May 25th. It terminated in southern Argentina. The payload was actually destroyed because the parachute failed to separate at touchdown. And I think here are some remnants we had from the flight. And fun story, people who actually recovered the hard drive, they had Jaguar bite mark in the hard drive. So, but the data was all safe. No worries at that. So yeah, so let's talk about what did we observe with this flight? What did we target? We targeted mostly 30 galaxy clusters. It's almost 35 to 40 galaxy clusters, all typical masses of 10 to the 14 to 15 solar masses, or low to mid redshift range. And most of the clusters are merging clusters. And I'm going to talk about this point a bit in the science goals part, because there is a reason the theory people actually wanted to observe the merging clusters, and they targeted only those. As you can see, these are
specifically targeted for the margin clusters.
Yes, exactly. And I'm going to give you the full list of the targets if it's interest to you, like if you want to play around with the data or something, at the finish of the talk. Okay, so these are the footprint here about the targets. It's all about around the sky. This is, I think you can see, right? Okay, still some light, but anyway, this is I'm giving you some sneak peek to the data taken by SuperBIT. This is bullet cluster. This is beautiful Able 1689. And this is, oh yeah, thanks a lot. So this looks much better now. Okay, 1689, this is Able 2163 with Hubble overlay. Yeah, you can turn on the light. It's okay. Thanks a lot. Okay, so now I'm moving on to the gravitational lensing part to give you some intuition about what gravitational lensing is. So if you have a distant galaxy that you are trying to observe, and the light is coming to okay. So if you are trying to observe a distant galaxy and the light is coming to you while interacting with the intervening dark matter or the mass distribution, the path of the light will be bent due to the curvature in the space-time. And you will see some distorted image of the background galaxy, as you can see in this plot. Here are some of the examples of lensing happening. These are all strong lensing. So these are very rare events where the background galaxy is at just behind the foreground mass. So you can see by eyes that there are some stretching happening. These are Einstein rings. It only happens if the light is in between the Einstein radius. But these are rare event, and this is not what I'm here to talk about. This is totally different thing. I'm here to talk about weak lensing, which is not so easy to understand. So, as I said, this is seen by naked eyes. This is seen by eyes, but here also some lensing is happening, but you cannot see it. It's not so obvious here, right? And you can only know that there is some lensing happening by doing some statistical averaging over the sky in this portion of the sky. To talk about some distortion due to weak lensing, it causes the background signal to background galaxy to magnify. That's called convergence. It's very hard to just measure the magnification, but what we observe is the shear, which is the distortion. So due to shear, what happens is that there is some distortion in this XY direction, and there is 45-degree angle direction. It's just convention, but you just need to understand to quantify this shear, you need 2 degrees of freedom. But this is easier to measure. This is easier to infer from an observation. But the problem is that here I'm showing you the background galaxy to be a circle, but that's not the case. That's never going to happen, that you have a face-on circular background galaxy. So that's the second point that I'm going to talk about. Each single galaxy that you're trying to observe, which you think might have gone through gravitational lensing, will have its own intrinsic ellipticity. And when you measure each galaxy's shape, there are two contributions. The first one is its intrinsic ellipticity, i.e., each galaxy has like different random orientation. And the second is the shear, due to which it has been distorted a bit. Good thing about the intrinsic ellipticity is it averages out to 0. So if you take significant amount of galaxy to average, you will see that it will go to 0. And that's what we can use to infer the weak lensing. So what we do, we take a portion, we measure individual shape of each of the galaxies in that portion. We average out, we take average shape of those galaxies, and that's what our shear is. Is there any question till that point? Okay. So by this time, I hope I have convinced you that it's really important to measure shape of every individual single point that you see in this picture. Okay, yeah.
Yeah, so the intrinsic liquidity will be averaged out to be zero. But does the shear, it is the total shear or it has individual values for individual values?
Yes, that's a good question. So you assume the region that you're taking average of, the shear will be constant there. So if you take, for example, all the galaxies together in the sky, the shear will also be zero because shear is not constant throughout the sky. So you have to take, so you have to understand the scale variability of your dark matter distribution, and in a way you have to kind of take pixel size, where you don't wash off the weak lensing signal itself. So that's a good point.
These galaxies, very close to, you have a constant shear field.
Yeah.
So you cannot have this projection effect.
Yeah. So
Take care of that also.
Yeah. So you can only have like so when we talk about, and I'm going to show you the dark matter distribution, there you can only attain to a very finite resolution of the dark matter because you have to take the pixel size in that way. But even if you, let's say, took a bigger pixel than needed, then you're just washing off the signal.
Yeah, I mean, RA and DEC, I think if they are part of the clusters, that should be fine. They should still have the same shear, ideally. But when I say close, I mean that they're actually identical redshifts to some degree. The redshifts has to be sort of same, otherwise, I mean, there can be this projection. I mean, when you're talking about the lens, projected image, they might look same,
Exactly.
but they have a different.
Yeah, exactly. So we do take only the background galaxies, and there it can have, of course, there is a redshift distribution for any telescope. But yeah, we have to take into account that redshift distribution. That is very important to measure the mass or the convergence. Not the convergence, but the mass.
I think you either take similar kinds of galaxies throughout, or you take all the galaxies and assume a teleoccupation model. And then forward model your weak lensing. For example, if you assume a constant shear, you would take only those galaxies, let's say red, so the red elliptical galaxies or white clustered galaxies, and then you would assume that they would be in similar potentials and given in small redshifts, and then I think the shear would be constant for those.
They are similar kinds. We are talking about galaxy properties.
Right.
Yeah.
The other kind of selection.
There are other kind of selections, but
potential field is identical.
Right.
Or similar.
yeah. Here, all I'm saying is whatever the background galaxies are, it's being lensed by one dark matter distribution. And I'm saying, like, in that dark matter distribution, the number of galaxies that you have, you can only give you that leverage to go to even higher resolution. But if you don't have like higher number density of the background galaxies, then you have to stick to bigger pixel size, because I'll talk about the galaxy density. Yeah, for the statistics, because if you don't take averaging over multiple number of galaxies, then you will not get shear. So I guess I lost track of where I was going with that, but let's move on. Thanks a lot for that. No. I'm not blaming. It's really important that please ask question. This is really interesting. Yeah, so this is the simulated lensing effect. As you can see, the background galaxies are being lensed, and there are strong lensing that is also happening, but there are also very subtle weak lensing that is happening here. So by this point, I think I have convinced you that shapes are really important. And this is what I was talking about. So since you have two components of the observed shape. You have one, which is the intrinsic ellipticity, which is much, much higher magnitude than the shear. As you can see, it's 10 to the minus 2, 10 to the minus 3. So you need a lot of galaxies to get a significant detection of the shear. So in principle, you would need 10 to the 3 to 10 to the 4 galaxies for a significant detection. That's never going to happen. But what you do is you take coherent distortion throughout the sky to understand if there is a lensing. But moral of the story is that you need a lot of galaxies. And you also need very precise shape measurement. So this is what I have worked on, the data processing pipeline or the shape measurement pipeline for SuperBIT, where in one end, the inputs are the single exposure images, and the outputs are the shapes and colors of every single galaxy. And I'm not going to talk about the colors because that's a whole other thing. And the colors are really important to understand what are foreground galaxies, what are background galaxies. Since you only have two-dimensional imaging, the color kind of gives you the information about the redshift, the distance from us. So you also need color to understand what are foreground, what are background. But I'm going to talk about mostly the shape today. So let's separate the pipeline a bit. So first one is stacking, then we do source extraction, and then finally we do shape measurement. So if I take the stacking, you will see the input are again single exposure images, and the output is a stack of 36 exposures. We have taken 36 exposures of each single target. And as you can see, the telescope actually moved for different exposure, and that's why we have this dither. These are telescope systematics that happen due to the rotation of the telescope during each single target. Yeah, this is only B band for now. Yeah. So for science, we have like U, B, and G, 3 bands. But I'm showing you the shape measurement in just B band. Yeah. Okay. So let's say you have a stacked image, which is 36 exposure stacked image, and you have to take into account all the rotation and everything, and you got your deep image of all the galaxies that there is. Now what you do is source extraction, i.e. you try to understand what are the sources there is in this image, and then you have to measure shapes. Now I couldn't put all the green circles here because it would make it really congested. So if I kind of try to zoom in to some region, you will see that each of the points that you see, it's not very easy to see here, but each of the green circle that you see, they're all sources. They're all galaxies or stars that you need in your analysis, that you need the shapes of, not the stars, but the galaxies. And like any other thing, there are some stuff which is a bit painful. It's not galaxies, but something else, like spurious detection around very bright stars. So that that red thing is a very nearby star, and it has diffraction spikes. So if you take an image of the sun, you will see that there are diffraction spikes in the image. And when you run your code to extract sources, it will extract sources in those diffraction spikes as well. So you have to do masking around those very bright sources. You'll also have to mask around the edges of the image so that there are no spurious detection in that region. There are things like hot pixel. The telescope had weird hot pixel, which also gave us like sources, but they are not sources. We had to take care of that using hot pixel mask. So let's say you have got rid of all the bad things and you are only left with galaxies and stars, and you only have like significant, like good detections, let's say. And now I'm going to zoom in to each of the objects to show you what they actually look like. So this is an extended object. This is actually image of a galaxy. This is another galaxy. This is another galaxy. There are also stars like these. So you have these observations from which you have to measure shape. Think about how hard it can be. This is just messy image of a galaxy and just stars. But you need also star as well, as I'm going to tell you in a bit. So all you have are these messy images of a galaxy and a star. Now you have some understanding about how did we get here? How did we get this observation? So we started from the original galaxy for which we didn't know the shape, right? For the star, however, we knew the shape, that it's going to be a point source. That information is known to us. Now, for the galaxy, it goes through gravitational lensing. It goes through a shear, and that's why it lenses. And then there is a blurring that is happening due to atmosphere and the telescope, and that happens to both the galaxy and the star, and it makes it blurry and a bit bigger. It's smeared than the actual image. Then there is a pixelization happening in the telescope because the CCD has like pixels. And finally, it adds up some noise to give you this final image. So what we observe is this. Now, for the star, you know the starting point and you know the observation. So you kind of know what the mapping that the telescope does to go from this image to this image, and that is called the point spread function. So from the star, you understand the point spread function of the telescope, and then you want to undo that effect on the galaxy. So your image of interest is this gravitationally lensed galaxy, and you want to undo the effect on that observed galaxy image. So you undo the PSF on the galaxy image to go to the sheared shape. Okay.
Isn't the whole.
Mhm.
Well, I think go ahead. I'm asking a more extended, but go ahead.
Okay.
You can discuss.
Okay. Yeah, so let's say you have observed the steps here, they are very much involved, and I'm not going into the details of this. If you want, you can ask me, how do we do this? But let's say you have observed and measured the shape of each individual galaxy. Then what you can do, first, let's go back to the source extracted image where you are trying to measure the shape of each individual point here, which are galaxy. And then after getting the shape, you can try to understand the convergence map. And I'm not going into the details of the case inversion technique. I'm just going to show you the first ever taken dark matter map from the stratosphere. And there it is. This is Able 3411, and the color map is telling you the dark matter concentration here. And it has been inferred from the shapes of each individual galaxies. And if I also put the X-ray data, which is coming from the hot gas in the intercluster medium, this is what it looks like. Have also some other pictures, I think. This is for bullet. The what? Is from the hot gas in the intercluster. Oh, from Chandra. Sorry, yeah, from Chandra. Yeah. So these are all from Chandra. Okay, I should have put that in the image. Sorry. Yeah, thanks. So yeah, what I was. Yeah. So these are all the maps that we have, and I'm going to show you the list that I have in a bit. But this is the pipeline that I was talking about, and
The cluster or the background? Right.
The background dots, they are the galaxies.
The background there.
This is basically the image of the coad, which has the background and foreground galaxies, but we had to separate out back.
Pipeline with
Yeah, exactly.
all of it.
Yeah, the background galaxies. If you're asking about the density per arc minute, it's like 17 to 20 galaxies per arc minute square.
That's the background.
Yeah, that's background galaxies. Foreground, like if you take the cluster galaxies, like 100 galaxies probably for the cluster. Yeah.
And the stars that you use for this
PSF, yeah.
thing, that is like a star in our galaxy that is at the right field and has the right kind of brightness. If it's too bright, then
Yeah.
it's a problem.
Yeah. That's a very good point. So, so this is what I do. Okay, let's see. Right. So you're exactly right about that intuition. So what we have to see, the y-axis here in this plot is the size of objects, and the x-axis is the magnitude. So if you go to the left, it's brighter. It's actually, yeah, this is astrophysics department, so you know magnitude, what magnitude is. So as you can see, for very bright stars, there are some stars which are appearing to be a bit bigger, but it's just due to the overflow of electrons to nearby pixels, and it makes it brighter. Makes it bigger, and you cannot take that for your PSF. So what you have to do, the thumb rule is basically you take 1.5 magnitude higher than the faintest saturated star, and you'd go to like SNR around like 20 or something to see what are the stars that you're gonna use. Yes.
What are the all point sources in your field?
Yes, exactly. So these are all good stars. So the red points, we say good stars. The red and green all are good stars, but what we do for the PSF modeling. So good thing, bad thing about the PSF is that it also varies throughout the sky. So the point spread function is not supposed to be, let's say you measured one star and that's it, you're good. That's fine. Everything is like that. No, not like that. So you have a PSF variability throughout the sky, and you have to understand that variation. Because at the position of your galaxy, you don't have a star. You don't know what the PSF is. You can only interpolate between two stars to understand the PSF at the position of the galaxy. So you need to understand how the interpolation is happening. So what we do, for all the good stars, we take 80-20% split, and for the 20% is reserved for testing the interpolation. So for the green ones, they are train star, let's say. We train our PSF model to use only those green stars, and we see how it's fitting at the position of the red star, and try to present the diagnosis in a quantifiable way, if that makes sense. So this is one example. Right. It's 0.46 arc second. That's the median. Yeah. So yeah. Yeah, it was supposed to be diffraction limited, but yeah, it was highly ambitious, but it's less than, bigger than that. So this is one of the example of the left one is actually an image of a star as looked by a telescope. And this is how we modeled the PSF, if that makes sense. And these are some quantities that we track to understand how the model has been fitted. For example, ellipticity, U1, E2, and the size, how big it is. And as you can see, the PSF varies quite a lot by, so this is basically the CCD coordinate. This is the camera chip that there is. But yeah, the point is it varies a lot. Anyway, yeah, that's a good point. Thanks. Okay, things I didn't get to talk about is one of them is the color information, i.e. the foreground background separation. That has been led by one of my student, Maya, who is at NYU right now. So what she did was basically use the color information from different bands. So we have 3 bands that we use, B, U, and G, and she used color information to separate out foreground and background galaxies. One of the things I also didn't talk about is a shape measurement algorithm that we are working on using CNN called ShearNet, which is done by Adam at WPI. And this is basically trying to model the deconvolution, the undo part that I talked about. When you know the PSF, then you want to undo that effect. And we have seen that usual Bayesian forward model that we use for SuperBIT causes a lot of PSF leakage, PSF electricity leakage. That's why we cannot take high elliptic PSF electricity regions. So we are trying to come up with a better shape measurement algorithm using CNN, if that's going to be useful for later telescopes. So about the science goals that I told you that I'm going to talk about, it's basically done by one of my collaborator at JPL, Julia Serini. And she's right now looking at simulation. These are all Bahamas simulations for different dark matter model. And what she's doing is trying to see the matter power spectrum and coherence between different probes of astrophysical things like the dark matter, the stars, and the X-ray, and trying to see how coherent they are, how all the three things kind of interplaying in the cluster in a quantifiable way, of course. Yeah, these are all simulation results. And our goal is to look at SuperBIT targets and try to see if we can put any constant using.
Sorry. Just to
Mhm.
clarify.
Mhm.
So she's using clusters in the simulations for the matter power spectrum?
Yeah.
So now she's saying that in the simulation you have galaxy clusters.
Mhm.
You look them through the dark matter, you look them
Through
X-rays,
X-rays and
stars.
stars. Yeah.
Then you reconstruct the matter power spectrum
Yeah.
from these three observables.
Yeah.
And try to
Exactly.
see
Exactly.
that what is the difference.
Exactly. So these are, I don't know if you can see this, but these are all different self-interacting dark matter model injected.
Dark matter.
Yeah. So you are trying to see the parameter using these probes. Yeah, she has a paper on TNG simulation. These are the results that gonna be there in future paper. And that's basically what we are hoping to do with SuperBIT. Bahamas. Yeah.
Exciting.
Yeah. And I'm gonna finish, okay. I'm gonna finish with this target list, which we observed with SuperBIT and the density. I don't know if you can see, I don't think you can see the numbers and the names, but if you are interested in looking at any of the target with SuperBIT data, please feel free to contact me, and thanks a lot.
Okay, so we have plenty of time for questions today.
Yeah, please.
Okay, Ori.
Yeah, so again, about going back to my previous question. That this shear you means that not the actual shear of the galaxy, but the distorted picture that we are seeing, right?
Yeah.
But as per, maybe I am understanding it a little bit wrong, but this shear is happening due to the lens.
Yeah.
And if we are saying that we are assuming the shear to be almost similar for the region and all that, then we are saying that in the region the dark matter distribution is almost similar.
Yes.
So we are actually not getting the full information how the dark matter is itself evolving inside.
Yes, exactly. Mhm. So that's why you need the source density I have quoted here. That's why it's important, because first of all, in order to understand if there is any weak lensing happening, you need to average out over multiple number of galaxies, good number of galaxies. Let's say, like, usually we do like 10, where the distribution is at least Gaussian, but you need that. So if you have low object density, you have to go to a bigger pixel, where maybe you are missing some dark matter distribution details, but that's the best you can do.
What can be the solution?
Object density. Object density. So better resolution. So it depends on the depth. So usually the bigger the mirror is, the more the deep the image is. Also the PSF. So usually Hubble or JWST, Hubble has I think 2.6 meter and JWST has I think like 6.5. So usually space-based telescope have like smaller mirror, but like the PSF is diffraction limited. There is no atmosphere, so you have more object density. But for ground-based telescope, you have like, PSF is very bad, but they can afford bigger mirror. But yeah, so that's the best you can do. And in order to get higher dark matter distribution, high resolution dark matter distribution, you need more object density.
Can I just have a comment on Orit's point? So
Mhm.
I think the point that Orit is trying to make is that if we assume a constant shear,
Mhm.
then we do not have the ability to reconstruct the dark matter field through the
At least in the
weak
region.
Yeah.
lensing observation. But that shear will not be exactly same. So it's
Mhm.
an assumption of
Yes,
shear, but then that can give us like the average.
exactly.
So if we assume that this is the average shear of the field, then we can have an average reconstruction of the dark matter field. But maybe your point is that
How can we make that?
make that better so that you can see like the evolving spatial evolution or whatever. Basically spatial evolution
Exactly.
of the field itself.
We are taking the spatial distribution. For a small region, they are assuming it to be constant.
That's what I'm saying. So
Yes.
if you look at
Even-
large region,
That's why they are getting the distribution.
yeah, but then the point is that if it's a larger region,
Mhm.
and if you have the same background galaxies,
Mhm.
then how do you know that how the shear field is going to vary?
Exactly. So again, you have to focus on what.
Yes.
Yeah, I was saying like you have to focus on what scale that you are trying to
Yes,
measure.
yes.
Like the plot that I showed you in this, this is the x-axis is actually the scale. It's the Fourier space. So with Hubble, you can go to very low scale. With DS or something, you go to very high scale. But it's okay. Like you have different science needs, right? So depending on what kind of physics that you are, let's say you are trying to measure S8 with higher precision, you don't need like probably like the small scales. It's okay. But let's say you are trying to see self-interacting dark matter. You need these
Really small.
regions. You need these regions, right? So you need to go.
What is the thing of SuperBIT? Which scales can it look at?
I think like right now it can go around like this amount 10 to the power 1 or something. I think I had a plot, but yeah. So we thought that we will get object density as good as Hubble, like 40 galaxies per arc minute square or something, but it's not the case. And the exposure quality varies a lot for different things. Maybe we saw that when the telescope was going through Andes around like South America, that the telecommunication was bad. The rolling star was not working. So to make the stability good, you have to use guiding stars, and sometimes that doesn't work, and so the exposure quality sometimes degrades. So yeah, that object density is very variable around different targets. These are that object density. These are not yet public yet, but this is going to be in my paper, which should come within like few weeks or so.
Okay, other questions? Abhijit?
We have a lot of galaxy we are getting analyzed.
Mhm.
Different galaxy of their own orientation and inclination angles.
Exactly.
So the inclination, the ellipticity we are taking about, is that the projection of the galaxy? Then how are we linearly adding the shear factor with it, because it's also related to the dark matter distribution.
What is CR factor right now?
The shear
Oh, shear factor. Okay. Yeah. Okay. So let's rephrase your question. So you are saying this is the observation the shape that you are measuring, and there are like two contribution. One is the intrinsic ellipticity, and then there is the shear. And you are asking, how are we separating out this shear, right? That's what you're asking. Did I? Okay, good.
And because since every galaxy have different orientation.
Exactly.
It should have different.
No, that's the thing. Like they might have different orientation. They are background galaxies. They are randomly oriented, but the field that they are sheared by is the same field, at least to the resolution that we. Yes. Yeah. No, we cannot. Yeah. It's the 2D projected because you can only see the 2D projected. Yeah.
That would be like in a field intrinsic electricity of galaxies is a 2D projection.
Yeah,
But even then, if you have large number of galaxies, that will average out.
exactly.
This is the assumption that is being made.
Yeah, and
If
that's
you average over enough galaxies,
yeah,
then the intrinsic shape, কোনোটা এদিকে কোনোটা ওদিকে হয়ে, it will be cancelled out.
Yeah.
So only the external applied shear, which is from the
Dark matter
gravitational
field.
field, that will remain.
exactly.
এজন্য অনেকগুলো average করলে it will separate out the.
And that is also not always the case because you don't.
Correlations.
Yeah, intrinsic alignment. Yeah, that is there.
That can affect the orientation. of
Yeah,
the
and also it depends on the color. Like red galaxies had more intrinsic alignment. That's a whole different thing. And we observed in blue. Anyway,
fast level of it.
yeah, there's a lot of level of assumption. But like very higher level thing that can go wrong is this, that your intrinsic electricity is like 2 times higher order than the shear that you're trying to measure. so you can understand. So when you average out, so this is supposed to be 0, but that's not 0. It has a distribution. So the scatter that there will be is sigma e divided by root n. So the more number than n you have, the lower your.
Just at the exam.
They had their statistics and data analysis.
Perfect. So you can understand how hard it can be to get shear signal to noise ratio like that. So yeah,
Other
thanks.
questions?
Good questions.
Okay.
You said a lot of time.
No, please ask questions.
But I'm not here yet.
The first question is, you mentioned that you expected to be diffraction limited, but it didn't. What's the reason? Stability is very good. That's almost like 1/10 of your
Mhm,
ESF that you are getting.
mhm.
What is the reason? And you are also above the atmosphere, almost like